Good morning, everyone, and welcome to the IBM Qiskit Live Quantum Seminar Series, which is now just called the Qiskit Quantum Seminar Series, I believe. Now, dedicated to you, the research and academic quantum communities. Now, in just a minute, I'll be thrilled to roll out this week's episode with Professor Sagar Vijay from UCSB. Before we get there, and I'm personally very thrilled about Sagar coming here, I'm so glad you joined us on time. Now, we have a tradition to give everyone just a minute or two to tune into the live stream. Meanwhile, it's really good time to get active in the chat. Reply, where are you guys tuning in from today? You know that that's my favorite question. Let's start in the comment chat box located on YouTube, somewhere here above, below, left or right on your screen, because that's the same place where you can ask questions live with Sagar and myself during the seminar, and we can have a lively, fun discussion. And we tend to have a lot of questions and answers and discussion going through the um, edutainment event, if you will. So, a few announcements, folks. We got some very exciting things coming up, quite a bit actually. Next week, on October 27th, we have a very, very special seminar with an introduction by the one and only Jay Gambetta, VP and Fellow of IBM Quantum, as well as four panelists who have recently unleashed some 100 qubit plus experiments for the community that will tell us about what it takes to be able to go to that precipice and be able to do things at the 100 qubit plus scale, why that's interesting, why it's important, how to get there, and what it means for the community and what it means for moving forward. So tune in, take a look at that. I think it's going to be a really exciting presentation. I'm very excited about it myself. We got quite a bit of interesting work coming out of that. Also from myself and the group here, we'll have a lot of things to say and discuss. And of course, as always, it will be live, so bring your questions. And also, more great announcements. We have a paper series that has been coming out, focusing on a few key papers and diving deep into what they mean, that is coming out on the channel. So take a look. With that, I'll remind you, this seminar takes place every Friday at noon Eastern Time, right here on the Qiskit YouTube channel. To know what's coming up, click like and subscribe. And with that, let's get to it. Okay, I'm your host, Zlatko Minev from IBM Quantum Research, and on this episode 142, I have the delight and privilege to introduce you to Professor Sagar Vijay from UCSB. Hello, Sagar. How are you today?
Hi, Zlatko. I'm great. Thanks.
Yeah, it's great to see you. Are you tuning in from sunny SB?
Yeah, from Santa Barbara. It's a gray morning here, but yeah.
All right. Well, Sagar, before we proceed, allow me to introduce you to everyone. Sagar is an assistant professor in the physics department at University of California, Santa Barbara since 2020. Sagar received his AB from Princeton in 2013, his PhD from MIT in 2018, and afterwards was a junior fellow in the Society of Fellows at Harvard University from 2018 until joining UCSB in 2020. Sagar, with that, welcome. The stage is yours.
Great. Zlatko, thank you so much for having me for this great seminar series, and to everyone who's watching this now. I'm very excited today to tell you about some relatively recent work about new possibilities for mixed quantum matter, so for open quantum many-body systems that are really made possible by incorporating some of the ingredients that are native to quantum simulator and quantum computing platforms, namely dissipation and adaptive feedback by an external observer. So these the new possibilities that I'll be talking about today, that I'll be covering, are summarized in the two papers that are shown on the slide up here, which I'd really encourage you to take a look at if you're curious. And I'd like to, before I start, thank my wonderful collaborators, Isabella Lovas and Utkarsh Agarwal, both postdocs at the Kavli Institute for Theoretical Physics, Zhihao Zhang, a graduate student at UCSB, and collaborators, at the Perimeter Institute, Peter Liu and Tim Shea. Right, so let's get started maybe with some background that's probably familiar to many of you who are tuning in. So when I think of a quantum simulator, I imagine a system of tens or hundreds of qubits, which are imperfectly controlled in the presence of noise, but with the broad goals, sort of two goals that I have in mind of quantum simulation are actually replicating quantum many-body physics, or trying to understand quantum many-body physics beyond maybe what we can classically simulate, and then also using quantum simulators en route to storing and manipulating quantum information, en route to building a quantum computer, right, where we can do some interesting manipulations with that quantum information that we know we won't be able to do classically. So there are many platforms where quantum simulation, as described, is being performed, including superconducting qubits, trapped ions, spin qubits, Rydberg atom arrays. The physical degree of freedom that forms the qubit is very different in each of these platforms. And the native capabilities also vary to some extent, though there's a common theme. Of course, in superconducting qubits, we have a Josephson junction that forms the kind of fundamental physical ingredient that's used to make the qubit, whereas, say, in spin qubits, it's the spin of a charge carrier that's used as the qubit, right? But while there's a sort of plethora of these platforms, these systems are, broadly speaking, controlled using some kind of interactive quantum many-body evolution. Some people refer to this as adaptive quantum many-body evolution, and this is evolution that proceeds through targeted unitary dynamics. By targeted, I just mean it's controllable by the external observer, by the experimentalist, to some in some meaningful measure. And along with that, there's measurements and possibly feedback. These are certainly capabilities that one would need to do something like active error correction, for example, but are also really interesting capabilities for generating quantum many-body states that we actually want to study on a simulator platform. So here's my caricature, which I'll refer back to for adaptive quantum evolution. I have some arrays of qubits that are being maybe frequently or infrequently observed by some external observer who's also in charge of the unitary evolution of that system. After performing some kinds of measurements, there might be post-processing of those observations on a classical computer, and that post-processing proceeds to some reasonable degree. And then subsequently, that informs the way that this observer is going to continue to repeatedly interact with this quantum many-body system. So that's my interactive or adaptive quantum many-body dynamics. And this is very interesting from a quantum many-body physicist's perspective, because it's not a natural way to think about quantum many-body evolution coming from quantum condensed matter physics, where we're really used to how thinking about materials that we probe near equilibrium, linear response at low temperatures, and that kind of to figure out some kind of inherent order. Whereas here, what we're actually doing is we're using observations and feedback to drive order in a system, to drive evolution that produces interesting quantum coherent and quantum collective phenomena. So the broad question that I want to focus on today, which I'll make specific in the next few slides, is really, what is the power of interactive or adaptive quantum dynamics to foster quantum collective phenomenon, even in a relatively noisy quantum device? And by noisy, I mean, and this is an ingredient not shown on the slide, that the quantum system that I'm interacting with is also coupling to an external environment in ways that I can't control, but are unavoidable. And even in spite of that coupling, I want to preserve quantum coherence. So how do I do that? And what is the power of interactive quantum evolution in doing that? What are the lessons we can learn for how we can actually do that? Okay, so the reason I'm interested in this question is actually twofold. And the first reason I'm interested in this question is in order to prepare new and highly entangled quantum states. And we actually know, and we've known for a while actually, that adaptive protocols where we do measurements and we condition a future evolution of a quantum system on those measurements can more efficiently prepare new and highly entangled quantum states compared to purely unitary non-adaptive evolution, where there's no measurements, there's no feedback at all. And this is probably might be well known to many of you, but the reason is very simple. If I give you a short-range entangled quantum state, which is just to say, maybe I have a product state of my qubits, And then I evolve it using a constant depth unitary circuit. So a relatively simple unitary evolution. Each qubit, say, sees a constant number of unitary gates that doesn't scale at all with the size of my system. The system I end up with after performing this unitary evolution will still be somehow short-range entangled. There won't be long-range correlations that I've introduced in the system. And the reason for this is because unitary circuits, unitary quantum circuit evolution has a very sharp light cone. If those unitaries are say, local unitaries, there's a sharp light cone. And beyond that light cone, I can't really introduce more correlations if the depth of the circuit is bounded, right? But that constraint, which prevents short-range entangled quantum states from becoming more than short-range entangled in the unitary context, is really avoided if we have adaptive evolution. So constant depth adaptive quantum circuits can produce, in many settings, possibly long-range entangled quantum states. And the simplest example of this, where even the adaptation is not something that we really need to care so much about, is I can take the ground state of commuting projector Hamiltonians of quantum many-body systems whose ground states have topological quantum order, and we can measure the commuting observables that uniquely specify eigenstates of that Hamiltonian, and in doing so prepare long-range entangled states, right? There I've introduced a new ingredient of projective measurements, which was absent, obviously, in this non-adaptive unitary circuit evolution, right? So that's a constant depth adaptive circuit that quickly prepares a long-range entangled state from a generic short-range entangled quantum state. And this observation has actually very recently been used, given the amazing progress that's been made in quantum simulators, to try to prepare non-abelian topological quantum orders, specifically a D4 topological quantum order. So D4 is the dihedral group of order 4, and this has been recently implemented in trapped ion platforms. And this has been made possible due to both theoretical progress in understanding adaptive protocols that can actually prepare non-abelian topological quantum orders, which are relatively complicated, and also in trapped ions, for instance, determining how to actually implement experimentally measurements and feedbacks and mid-quantum circuit measurements that are sort of necessary to realize these entangled states. Of course, preparing this entangled state is interesting for theoretical reasons. We've prepared some exotic, in this case, highly entangled state that we'd be hard-pressed to find in nature, but it's also very interesting because some of these non-abelian topological orders, their ground space can potentially be used to come up with, say, quantum codes that can robustly store information in the presence of some active error correction. We might even be able to manipulate that quantum information and perform some fault-tolerant gates, right? Okay, so these are all protocols, or largely speaking, these adaptive protocols like the one that I showed on the screen are ones that are designed to prepare targeted quantum states of many-body systems. So these are described by pure wave functions, but we know that that might not be the most generic thing that we can expect in a quantum simulator when the device we're thinking about is coupled to an external environment, and also if it's actually just hard to come up with an adaptive protocol that converges onto a particular pure state. So if the feedback doesn't actually converge onto a pure state, is it still possible to prepare mixed quantum many-body states with very desirable properties that we want in quantum pure states? And those desirable properties are long-range correlations, quantum criticality, or long-range entanglement, right? So maybe preparing a specific quantum state is too stringent of a requirement, but we just want to prepare quantum many-body mixed states or other states more generally that have some targeted correlations or entanglement that are universal, right? So what are protocols that realize, adaptive protocols that realize mixed quantum states with these desirable properties? So that's one motivation for studying these kinds of dynamics. The second motivation is more fundamental from the standpoint of quantum many-body evolution, which is to ask, if I view the tuning knobs in a quantum simulator, adaptation, dissipation, unitary evolution, as just fundamental ingredients in quantum many-body dynamics, what quantum many-body phenomena are possible in open quantum evolution in this kind of quantum evolution, which proceeds for a sufficiently long time. So previously we talked about constant depth adaptive protocols, which are, evolving a quantum many-body system, say, for a very short amount of time. But we could ask, what do these ingredients do for us as far as long-time quantum many-body evolution? What kind of quantum coherent phenomena can be fostered, if any, right? And the simplest question is to ask this even without adaptation, right? So if I just have unitary evolution and some non-unitarity, like coupling to an external environment, or just measurements by an external observer, but no adaptation, then what quantum collective phenomenon can be fostered? And this question was, I think, first asked, some number of years ago now in 2019. And one very interesting answer to this question is the measurement-driven entanglement phase transition, which I think was first discussed in these papers, where one imagines that one has a quantum many-body system that's evolving with local unitary gates, but also evolving with local measurements by an external observer with a tunable rate per unit time. And well, we know that if we have a quantum system that's initially not very entangled, that evolves according to local unitary gates, and those unitary gates are sufficiently generic, in the absence of measurements, that quantum many-body system at very long times will be very highly entangled. At very, very long times, it'll really resemble a random state in Hilbert space. But we also know that if we didn't have any unitary evolution at all, and we just performed local projective measurements, that we would sort of arrest the evolution of the quantum many-body system and prevent it from becoming entangled at all. Measurements have the effect of disentangling, of competing with the formation of entanglement, right? So, this kind of observation leads to the question, well, after a long evolution, how entangled are states within a given trajectory of measurement outcomes as I tune the rate of local measurements that are being performed per unit time? We know the answer when this rate is 1, we're always performing measurements, or we're not performing measurements at all, but what happens in between? And the answer is kind of interesting. In a 1 + 1 dimensional quantum many-body system, as was found originally in these papers, if the rate of projective measurements per unit time is sufficiently small, then the pure quantum many-body states that are obtained via such an evolution have a very large amount of entanglement, quantifiably large amount of entanglement. The von Neumann entanglement entropy of these pure states within a region has what's known as a volume law scaling, so there's extensive entropy. But if the rate of projective measurements, or the rate of measurements, is tuned beyond some threshold, a non-zero threshold, then the pure state trajectories of the system cease to have a high degree of entanglement, volume law entanglement. They have what's known as area law scaling of the entanglement, which in one dimension means that the entanglement of a region just is a constant. It's not extensive to leading order. And this is a very interesting observation. There's been a lot of work to understand the nature of these two phases, the nature of the critical point, et cetera. But there's a drawback to sort of studying this kind of evolution in real quantum simulators in quantum computers. And the issue is this what I'll refer to and what is referred to in the literature as the post-selection problem. So we found an interesting quantum many-body phenomenon that occurs, a phase transition in the entanglement of pure state trajectories of a quantum many-body system that's evolving unitarily and in the presence of measurements with a tunable rate of measurements. But observing this in an experiment would seem to require post-selecting on the measurement outcomes. Why is this? Well, to address the entanglement entropy of an evolving wave function that is obtained through an evolution where I have performed measurements, well, I want to prepare the same state multiple times in order to determine the entanglement of, say, a subregion of that state. But doing so in different runs of an experiment would require post-selecting on the same observations of the state during the dynamics. And since the number of observations scales extensively with the space-time volume of the dynamics of this quantum circuit, it just does not at all seem practically feasible that that's something that one can do in a scalable way, right? And nevertheless, there are some very intrepid people who've actually tried this on 14 superconducting qubits. So even in that setting, it required thousands of hardware device hours over multiple quantum processors, that might even be a quote from the paper, to see something that resembled this kind of phase transition. So it's actually still an open question in the most generic setting whether this post-selection problem can be overcome to see this truly quantum phenomenon and the interplay of measurements with quantum evolution, right? Okay, so the question that this begs is, what other dynamical phases and phase transitions in open quantum dynamics, potentially involving measurements, that are similar in spirit to the measurement-induced phase transition exist, but which don't necessarily encounter this post-selection problem? Okay, so with these two motivations in mind, so quantum state preparation and just fundamental questions about quantum many-body dynamics, I just want to give an overview of what the rest of the talk will be like. I'm going to mention two, I think, exciting examples to me about how adaptation or dissipation can induce new kinds of mixed state quantum orders and phase transitions that make some progress in addressing both of the questions that I mentioned. The first part of my talk is going to be about how just measurements and unitary feedback can give rise to constant depth protocols where one can foster criticality, long-range entanglement, and potentially long-range order in inherently mixed quantum states. And this was recently published in PRX Quantum, and some follow-on work to this is also being completed with my student that I'll mention. The kind of mixed states that are produced through these protocols are inherently non-equilibrium states with both an extensive entropy, which also coexists with interesting long-range order and long-range entanglement. So it's potentially a new class of quantum states that I think deserves a lot more thought, a lot more exploration. And the second part of my talk is going to be about how unitary evolution in the presence of dissipation alone, so this is just the competition of some closed quantum many-body evolution, but now in the presence of an external environment, so everything is open. One can actually, even in this setting, in the absence of ingredients like measurements by an external observer, observe quantum dynamical phase transitions that are similar in spirit to the measurement-induced phase transition that are potentially observable without this kind of post-selection issue. And I will refer to these as coding transitions. These are dynamical regimes of quantum many-body systems that function as emergent quantum memories, where they can either preserve information or they lose all of some initial quantum information to an external environment, depending on the strength of dissipation versus unitary evolution. So that's summarized in this paper that's posted on the archive. So without further ado, the sort of long prelude, let me dive into some of these constant depth protocols that I'd like to discuss for how adaptive quantum evolution can produce new kinds of mixed states and orders in mixed states of quantum many-body systems. So let me just dive into a one-dimensional quantum many-body system that many of you might know very well from a variety of different contexts. This is the one-dimensional cluster state. It's the ground state of a Hamiltonian, which I've written on the screen. And this involves a periodic chain of qubits. The qubits live on sites indexed by J. And the Hamiltonian whose ground state gives me the cluster state is shown on the screen. It turns out to be a commuting projector Hamiltonian. This Hamiltonian is special for a variety of reasons. The ground state is special for a variety of reasons. One reason, as someone who does quantum many-body physics, that it's interesting is that the Hamiltonian has some on-site global symmetries. So this Hamiltonian commutes with these operators, these unitary transformations. The unitary transformations you can think of as flipping the qubits in some basis, in the Pauli sigma z basis, on even sites or on the odd sites. So that's G sub A and G sub B. So I might refer to these as the A sublattice of the system or the B sublattice of the system to refer to odd and even sites on the chain respectively. So this relation holds that these unitary transformations commute with the Hamiltonian. So that's fine. We know that so that's a global symmetry of the Hamiltonian. But interestingly, the ground state, this cluster state, provides an example of what's known as a symmetry-protected topological order. And all that means is that the ground state is some short-range entangled state. It's a wave function that can be prepared starting from a product state via a constant depth circuit. So it's not that complicated to prepare. And a constant depth unitary circuit. So there's no adaptation here at all. So it's really a very simple wave function. Nevertheless, the ground state is symmetric and unique when I have periodic boundary conditions for these qubits. So this is a gapped, unique, and symmetric ground state. And symmetric just means that it satisfies this condition here. And the fact that it's a non-trivial kind of symmetry-protected topological order just means that this ground state, the cluster state, is actually in a distinct phase from a symmetric product state, which, for example, is the ground state of a Hamiltonian H prime, which is trivially gives me a ground state, which is just a product state on all sites, which is also manifestly symmetric. But it's in a distinct phase if I preserve the symmetry. So what does that mean? In practice, it just means that if I gave you this cluster state and I perturbed it with some local, sum of local operators, and that perturbation was sufficiently weak, and the perturbation commuted with these symmetries, I wouldn't be able to close the gap, and I wouldn't be able to deform this ground state into, say, the ground state of the Hamiltonian H prime. I necessarily have to close the energy gap and go through a quantum phase transition if I preserve the symmetries. Another way of saying this, without reference to the Hamiltonian, really, is that there's no adiabatic evolution of this ground state that one can perform while preserving the symmetries that takes me to this state, right, where I have a symmetric product state. So in the presence of symmetry, there are many states, quantum many-body states like this that can exist. Nevertheless, this is a short-range entangled state. It's easy to prepare using just a constant depth unitary circuit. But the order, the fact that this is a symmetry-protected topological state, so the cluster state is just one example, one point in a larger phase diagram where the ground state of this Hamiltonian perturbed by symmetric perturbations hosts symmetry-protected topological order. And this kind of order is actually diagnosed by hidden quantum correlations, I should say, which are actually rather complicated to look at. So if we had a ground state, for instance, that spontaneously broke the Z2 cross Z2 symmetry, there might be long-range correlations in local operators that diagnose that spontaneous symmetry breaking. But the SPT order is diagnosed by a very different kind of correlation, which is the product of Pauli operators on whose support forms a kind of string over many sites on the system. So here, the index here just refers to sites on this lattice, and I have two different kinds of string-like operators. And as the size of the string becomes very, very large, so as I take the limit n goes to infinity, these correlations asymptote to some constant in this symmetry-protected topological phase. Now, in the cluster state specifically, this SPT order is such that these correlations are actually just this is exactly one in the cluster state. But if I just perturb this Hamiltonian generically with symmetric perturbations, I would still get some constant, in the limit that this index n goes to infinity. Okay, and this just seems very bizarre if we don't, without some physical reason for it. It just seems like some pathology. But physically, it's actually saying something very nice, which has been summarized years ago in this nice paper, that this kind of order is representative of the fact that this symmetry-protected topological state, including the cluster state, can be understood really as a condensate of domain walls of one of the symmetry, say GA, which is one of the Z2 symmetries. But this condensate of domain walls are bound to excitations which are charged under the other symmetry. So this is a very different way to prepare. This is very different from, say, how one would think about the trivial symmetric state, which is distinct from the cluster state, the cluster SPT state. There, one would just condense domain walls of both symmetries, and they're unrelated to each other. They both sort of condense independently, and one obtains a trivial symmetric state. But here, the domain walls of one symmetry carry charge under the other symmetry, and that's sort of the explanation for this order parameter. It sort of diagnoses the non-trivial nature of that kind of condensate. Okay, so why am I introducing this cluster state? Well, it turns out there's a constant depth adaptive protocol which converts the cluster state, which is, as I mentioned before, a short-range entangled state, into a long-range entangled cat state. So if I take this ground state, this cluster wave function, which can be prepared via a constant depth unitary circuit, it turns out there is an adaptive protocol that's constant depth that'll convert it into this state which is looks like the sort of symmetric state that one would get within a subspace, in a quantum many-body system where you've spontaneously broken this Z2 cross Z2 symmetry, right? So this is a macroscopic superposition of the spins being all up or all down, and this kind of cat-like state, Schrodinger cat-like state, is long-range entangled, right? It's not, it's somewhat fragile also, but it's not that easy to prepare given some short-range entangled state initially. And the fact that there is such a constant depth adaptive protocol can be understood in two complementary ways, either of which might be familiar to some of you. Well, the first is that it's been known for quite some time that the cluster state is actually a resource for measurement-based quantum computation. And that just means that if I rewrite the cluster state as a matrix product state, then measurements of the spin degree, of the qubit degrees of freedom in a special basis can give rise to a unitary evolution on the bond dimension space. And so I can think of the evolution of the of states in the Hilbert space of Hilbert space dimension given by the bond dimension of this MPS as evolving under some unitary circuit where the precise unitaries are determined by the measurement outcomes. And the fact that one can do this, and one can actually implement, as has been known for a while, feedback to perform deterministic unitary evolution in this bond dimension space implies that one can actually teleport the quantum states across the length of the cluster chain, which would require long-range entanglement. So it seems reasonable that an adaptive constant depth protocol could prepare something like a cat state. But here's a very simple argument, I think, for why one can convert the cluster state into a long-range entangled cat state that only really makes reference to the string order that I discussed earlier. And here's the protocol constructively, maybe with some subtlety, which is that I'm not going to discuss the adaptation. So I give you the cluster state, and what I do now is I measure the Pauli sigma x operator on each odd lattice site to obtain some measurement outcomes, which are packaged in a vector, which I'll call m. And if I think about, go back to the previous slide and think about the string order that exists in the one-dimensional cluster state, well, I've measured out the Pauli sigma x on all of the odd lattice sites. So the fact that there's this kind of string order here, in the second line, implies that after measuring out the sites in the Pauli X basis on the odd sites, I should have long-range order in the Pauli sigma Z basis on the even sites in between, right? And that's sort of just a consequence of the string order. The string order gets reduced to a much simpler order, which is order in the Pauli sigma Z basis across sites that are very well separated, right? Now, the state that I have obtained after doing these measurements is pure. So I'm picking measurement outcomes, which are labeled by this vector m. And the resulting pure quantum state has these correlations, Z0 and Z2n, for instance. Those correlations asymptote to a constant at long distances. Now, that constant depends on the measurement outcomes, and that's a subtlety I won't get into right now. But also, the protocol I've described, which just involves measurements on the odd lattice sites, is actually manifestly symmetric. It manifestly commutes with the GA and GB symmetries, the Z2 cross Z2 symmetries of this one-dimensional system. So as a result, the pure quantum state that I end up with is one that has both of these properties. It's a pure state where the state is symmetric with respect to both symmetries, both of the Z2 cross Z2 symmetries, but it also has long-range order in the sigma Z basis on one sublattice, right? And if it has both of these properties, long-range order on this one sublattice, and it's symmetric, you would say, well, the pure state is probably cat-like, right? Now, the hidden order has therefore been converted into long-range entanglement. The precise long-range entangled state, however, depends on the measurement outcomes m. So in order to actually prepare deterministically this cat state that I've drawn on the screen, I have to do some adaptation. I have to take the measurement outcomes. I have to apply some unitary circuit on my state. And it turns out remarkably that that's actually possible, right? So the hidden order is really only deterministically converted into long-range entanglement after that adaptation step, but that's not shown on the screen. But instead of trying to deterministically prepare a particular pure state in an adaptive protocol, let's just see if we can prepare a long-range entangled mixed quantum state using a constant depth adaptive protocol. And let's ask this question away from the cluster state wave function, right? So as I mentioned to you before, I can take the cluster state Hamiltonian and perturb it with some perturbation which commutes with both of the symmetries. And I demand that it commutes with the symmetries. If the perturbation is sufficiently small, I should still have this kind of string order that I mentioned in the ground state. Can we still apply some kind of protocol to turn the ground state for a value of G, which is this perturbation, into a mixed state that has a long-range order and also long-range entanglement? And the answer is, remarkably yes. How I want to think about this is as follows. So the constant depth adaptive protocol that I want to think about defines a quantum channel, which many of you are, I assume, very familiar with, which will prepare a mixed quantum state. And a quantum channel is just describing the generic evolution of a density matrix that's allowable under quantum mechanics. Any quantum channel, such allowable evolution can be decomposed in terms of what are known as Krauss operators. So that is, the constant depth adaptive protocol produces a density matrix that can be decomposed in the following way in terms of the initial state, which I fed in, which is the ground state of this Hamiltonian, right? K sub mu are the Krauss operators, and they satisfy this condition known as the Krauss condition, namely K dagger mu K mu. The sum over mu is given by the identity operator. Okay, and this is sufficient to guarantee both the preservation of the trace of the density matrix and positivity. And so I want to think about constant depth adaptive protocols, which are a sort of special kind, would give rise to a special kind of choice of Krauss operators for this channel, but that might produce some kind of long-range entangled mixed state. But the strategy here is going to be very similar to what we did for a pure state. So what we might want to ask is the following more refined question, which is there a set of Krauss operators corresponding to a constant depth adaptive protocol that both respects the Z2 cross Z2 symmetries of this 1D cluster state and establishes long-range correlations in the sigma Z basis? That is, after I perform this adaptation, I obtain a density matrix that satisfies this condition that I'm mousing over right now. In the Pauli sigma Z basis, say on the even sites, I obtain long-range order, right? And of course, if the density matrix here were pure, you would say that the pure state is cat-like if both of these conditions are satisfied. But remarkably, if both of these conditions are satisfied for a mixed state, rho, a mixed many-body state, then we can actually show that this density matrix is actually not a convex sum of short-range entangled pure states. So a given any density matrix can be decomposed in not a unique way as a convex sum of pure states. And so it's in general not a trivial thing to show that for any decomposition, the ensemble of pure states that we decompose the density matrix into is not short-range entangled. But in this case, we can actually show it given these two conditions. So this is really a sufficient thing to look for, right? So here's an example of one such protocol, and this is more or less borrowed from what we know we can do for pure states, for the cluster state to deterministically convert it into this GHZ-like state. So the protocol is the following. We take the ground state of this Hamiltonian for some sufficiently small g so that I still have SPT order. I measure the Pauli sigma x on all, say, even lattice sites to obtain some measurement outcomes. And then I apply some single site unitary operations on the odd sites, which are conditioned on these measurement outcomes, okay? And the conditioning is shown on the screen. So on every odd site, 2j plus 1, I apply the Pauli sigma x operator if the parity of the outcomes obtained on the even sites to the left was odd, and I do nothing if the parity was even, okay? So this is certainly an adaptive protocol. It's actually also an LOCC protocol, but it involves non-local classical communication. So very distant measurement outcomes in the Pauli X basis are required in order to, quote unquote, compute what the unitary is that needs to be applied on a given odd site, right? But the protocol only involves single site measurements and single site unitary gates, right? So that's it. And this protocol is fixed, and I'm just going to feed into it ground states of this Hamiltonian and see what happens, right? Okay, so So does this protocol actually satisfy the conditions that we want it to satisfy? Well, indeed it does. The operations involved, which are measurements in the x basis and unitaries in the x basis, or no unitary at all, manifestly commute with the symmetry. So that condition is satisfied. And one can further check that the Krauss operators for this channel, were one to write them down, satisfy a very interesting condition, which is that if you apply the Krauss operators to operators of this form, so if I take sigma z1, sigma z2n plus 1, and I apply these Krauss operators to this operator in the particular form that I've shown on the screen, then you actually produce deterministically this string operator that's also shown. So it sort of fills in between z1 and z2n plus 1 Pauli sigma x operators that act on the even sublattice. Okay. Why is that important? Well, it means that when I compute correlations in the z basis in this mixed state that's obtained through this adaptive protocol, I can actually equate that to the string order in the original wave function before the adaptive protocol was applied. So put simply, the ZZ correlations in the resulting mixed state are exactly equal to the string order in the original pure state, right? So manifestly, this is a protocol that works anywhere within the symmetry protected topological phase, which would be present as long as G is sufficiently small. So to summarize, anywhere within this SPT phase, it turns out we can produce a mixed state that is long range entangled and has long range order. Because of the fact that we have a symmetric protocol that produces, long range order in a basis which is off diagonal with respect to that symmetry. Okay. Okay. So to summarize, as long as the wave function hosts the SPT order, a constant depth adaptive protocol produces a long-range entangled state with long-range order in sigma z. But this is remarkably despite the fact that the resulting density matrix actually has extensive entropy. So if one computes the entropy, you trivially would find that due to the inherently random outcomes of the measurements on the even sublattice sites, the density matrix would sort of inherit extensive entropy, right? Nevertheless, that coexists with long-range entanglement and long-range order in sigma z. So what happens when we leave the SPT phase? So due to sort of time constraints, I can maybe go through this a little bit quickly. So for concreteness, I can consider the cluster state Hamiltonian perturbed by operators, which would drive me into a phase where G large enough that spontaneously breaks the Z2 cross Z2 symmetry. So I start in a phase which is the SPT state, and as G is tuned actually across G is equal to 1, I would go into a ground state which spontaneously breaks the symmetry and is no longer in the SPT state. Now, for ground states parametrized by this G, if I apply this adaptive protocol, what do I find? Well, it turns out you find a long-range entangled mixed state, and that long-range entangled mixed state loses its long-range entanglement and long-range order as you go across this quantum phase transition for the pure state that's being input into this protocol. And this can actually be understood in a very nice way by purifying this mixed state. So it turns out that this mixed state, any mixed state can be purified in a non-unique way into a wave function involving more in a larger Hilbert space. And one such purification here is one can actually take this density matrix rho of G and purify it into the ground state of this Hamiltonian that I'm showing on the screen, which is more or less the dual of this Hamiltonian. It has basically G, you can think of it as having G replaced by 1 over G, essentially, right? And then the density matrix here is actually obtained by taking the ground state of that dual Hamiltonian and doing an extensive bipartitioning of the system. So tracing out half of the sites where those sites that are being traced out are, say, the odd sites or the even sites, and then one obtains a density matrix on the remaining sites of the system, right? So this kind of, gives some intuition for how extensive entropy can coexist with long-range order and long-range entanglement, right? An extensive bipartition of an area law entangled wave function can still give you a density matrix with extensive entropy. Nevertheless, that density matrix can still give you long-range order if that long-range order were present in the original pure state. So that provides some intuition. Now, at the critical point, something very interesting happens. So we tune G to be 1, and we feed that critical quantum state into this protocol. And one finds a density matrix that exhibits truly quantum critical behavior. That is, if you look at correlations of local operators and of string-like operators in this density matrix that's obtained when G is equal to the critical value, GC, which should be maybe corrected on these slides, then one finds that those correlations decay as a power law in space. But remarkably, the power law decay occurs with a different exponent, different power, than in the pure critical point for this Hamiltonian. So this is different than if one were to compute the same correlations in the ground state of this Hamiltonian without any adaptation at all. And the entanglement negativity of this mixed state also exhibits behavior that's consistent with quantum criticality, in the sense that if one takes the entanglement negativity of a subregion of this density matrix, one finds that it grows logarithmically in the size of that region when the size of the region is sufficiently large, with a prefactor which is a bit of a mystery to us, because this prefactor is known to be, say, a quarter for the ground state of this Hamiltonian. But for reasons that we don't understand entirely, it's a different number when we do this adaptation and obtain this critical mixed state. Now, this, I want to emphasize, this mixed state that we obtain at the critical point is really, I think, kind of interesting, because a logarithmic scaling of the entanglement negativity coexisting with extensive entropy of the mixed state is not possible in thermal equilibrium. In fact, it's known that in a thermal density matrix, it's natural to get extensive entropy, but the entanglement negativity should always obey an area law scaling, as has been known for some time. So this is really a truly out of equilibrium state that we've prepared through some short depth adaptive protocol, which is long range entangled. Okay, so in the interest of time, I'm going to sort of move on and say that this kind of adaptive protocol can be used to manipulate critical quantum states as well, to turn them into other kinds of quantum states. So we can apply this to Luttinger liquids, as we do in our paper, to essentially foster ground states of systems where essentially what the adaptive protocol has done is it's allowed for the quantum mechanical degrees of freedom to sort of interact in ways that weren't possible pre-adaptation. And we can also get criticality in these constant depth adaptive protocols with non-local classical communication if we start with a gapped quantum system. So I can sort of state the result, which will be hard to convince you of maybe in the limited time. But in the previous protocol that I discussed, we really converted the SPT order, which is a gapped quantum order, into a density matrix, into a mixed state with long-range correlations in the sigma z basis, which one might also think of as being related to a gapped quantum order, namely symmetry breaking order, right? But you could ask, like, can you obtain critical quantum states or critical mixed states from a gapped pure state by doing constant depth adaptive protocols with non-local classical communication? And we can show that this actually isn't possible in one dimension. And the reason is because one can evaluate entanglement monotones that tell you that because the protocol that we're applying is LOCC, that the resulting state that we obtain is not one that can have, say, logarithmic scaling of the entanglement if we started off in an area law entangled state, which is what we would expect were the initial state gapped and in one spatial dimension. But in higher dimensions, this is possible, because in higher dimensions, critical pure states, so states harboring correlations that decay as a power law in space, can still be area law entangled, and gapped quantum states are also believed to be area law entangled as well. So this conversion is possible. And a neat example of this that we have is one can actually take sort of an entangled area law entangled, but also long-range entangled initial state, which is that of two Chern insulators with opposite Chern number. And one can apply local measurements, local unitary operations conditioned on non-local measurement outcomes to convert this into a mixed state with extensive entropy, but where the degrees of freedom, the remaining degrees of freedom in this density matrix, have some power law correlations. And those power law correlations are really inherited, again, as they were in this SPT example, from a kind of hidden order that exists in these Chern insulators, or more generally in quantum Hall states, where one can think of many quantum Hall states in terms of a composite particle, which is a kind of a bound state of an electron with some number of flux quanta, and for say the integer quantum Hall state, binding an electron to a single flux quantum produces a boson, which when condensed gives one this integer quantum Hall state, and it's the quantum channel that's being applied is one that really teases out this very hidden non-local order by doing local operations, but conditioned on non-local measurement outcomes. But more broadly, the power of non-local classical communication in restructuring quantum correlations remains really to be understood outside of the examples that I'm providing. Okay, so the final, the second example that I'll provide of how feedback and dissipation can really induce new kinds of quantum correlations is going to be sort of in the opposite limit. So we talked about how adaptation can produce new kinds of mixed quantum states. And we could also think about no adaptation at all, but just unitary evolution in the presence of some kind of dissipation, and ask what happens to quantum many-body dynamics when unitary evolution and dissipation compete. Is it possible that there are non-trivial sort of dynamical regimes or phase transitions that can happen even when the unitary evolution and the dissipation don't obey any particular symmetries, don't respect any particular symmetries? So I'm not looking for dissipation to stabilize particular ordered states of the quantum many-body system or anything like that. I'm just asking a very simple question, which is it possible that there are open quantum dynamics where there is actually a threshold of the dissipation strength beyond which quantum information in the original system is sort of stolen? And so I'll refer to this as a quantum coding transition. And the punchline of this is that the answer is really yes. So in an otherwise unitarily evolving system, dissipation can actually drive regimes of out of equilibrium quantum and many-body evolution, which act as emergent quantum memories. That is, they can preserve initial quantum information. And cranking up the dissipation strength can drive one into phases where this quantum information is completely lost to the dissipative environment. So this is in the absence of any kind of active error correction. And examples with active error correction are obviously well known, namely, in say like the toric code with a sufficiently low single qubit error rate. It's been known for a very long time that one can perform, say, measurements and feedback and really stabilize the code space of the 2D toric code. More recently, it's been shown that even in a short depth, or in a constant depth evolution of the toric code, coupled to some ancillary degrees of freedom. So you can think of it as the toric code subject to a single round of local decoherence. There's actually a threshold for the decoherence above which the code space of the toric code really becomes destroyed. That is, the information encoded in the ground space of the toric code is lost to these ancillas completely, above some threshold. And the result that we have is actually doesn't have to do with these sort of single rounds of local decoherence or constant depth evolution. It's really saying that a generic quantum many-body system in one dimension, subject to a sufficiently low rate of decoherence at its boundaries, will actually have such a quantum coding transition. That is, where quantum information initially locally accessible in the system will be lost to the dissipative environment above some kind of threshold. The reason I mentioned this result sort of in the same breath as the measurement-induced phase transition is because the MIPT is also a coding transition, one that is, of course, hard to observe because of the post-selection problem. The question that one asks is whether initial quantum information in a system evolving according to unitary gates and local measurements is actually lost to the observer who's doing the measurements, or if it remains in the system. And if the measurements are performed frequently enough, then that answer turns out to be yes. Okay, and this I think is also an interesting result because we know that here the decoherence that I'm thinking about is boundary decoherence that affects a chaotically evolving quantum many-body system. Of course, we know that if one takes like the 1D repetition code or something, then in general, if I forget about the error. If I forget about symmetry or anything like that, the 1D repetition code can really only protect classical information in the most generic setting, for a sufficiently low error rate. Nevertheless, if you have boundary decoherence and with no symmetries at all, it turns out you can protect some amount of quantum information. And the setup is actually relatively simple. So one imagines a long chain of qubits. So these are the qubits are shown, say, in green, and they're initialized in some very simple state. You can think of it as a product state. And the quantum information that initially lives in that system that I want to track to understand whether it's lost to a dissipative environment or not, I'm going to think of by entangling this short-range entangled state with some reference degrees of freedom, some ancillary degrees of freedom, which I'll call R. And I'm going to ask, as this system evolves according to some fairly generic local unitary gates, so for our purposes, we can even think of these as random local unitary gates in a one-dimensional system. In addition to that, some kind of boundary noise. So you can think of depolarizing noise or your favorite kind of generic dissipation that acts within some constant window near the left end of the system or the right end of the system. What happens to this quantum information? Does it get leaked into the environment or not? And there is a rich phase diagram here as a function. Say if I choose the depolarizing channel there's a very rich phase diagram for this coding transition as a function of p, which I'll maybe review. And the phase diagram is actually as follows. So I have this one-dimensional system. At every unit of time, each qubit sees order 1 number of unitary gates that couple it to its neighbors. And each qubit near the boundary is also just as likely to see some kind of depolarizing noise with strength parametrized by p. Okay. And I evolved this system for a time that scales linearly with system size. So this is a very deep quantum circuit. And I ask the following question, which quantifies what I've been saying earlier, which quantifies the question of whether quantum information in the system initially remains in the system or not. And that measure is the quantum mutual information. So I can ask whether the mutual information between these reference degrees of freedom and the entire system A is 0 or non-zero at late times. And it turns out that if I fix time to be some to scale linearly with the system, so I have a linear depth circuit where that constant of proportionality is fixed. So I'm looking at a sort of horizontal cross-section on this phase diagram. Then there's always some critical strength of the dissipation acting on the boundary, such that above that strength, the information is completely lost to the environment. And below it, the information is always at least partially protected. So the mutual information between the reference degrees of freedom and A asymptotes to a constant, a non-zero constant, in the limit that T and L go to infinity with, say, their ratio being fixed. The blue and red lines are actually just denoting the different natures of this phase transition, which I unfortunately won't have time to get to. But very interestingly, there's a kind of continuous phase transition that happens when T over L is a constant, but still a sufficiently small constant, and a very different kind of transition that happens when T over L is large. You could ask, this information is only partially protected, so some of it is lost to the environment, as opposed to this phase where it's completely lost. Can I fully protect the information in this phase? And the answer is yes. If the quantum information is initially encoded, so if I add an encoding step before the dissipation is turned on, and you can imagine that this encoding is done in some very generic way. So it's done via a random local unitary circuit with some depth, which I'll call T scrambling. Then the phase diagram is actually slightly different. So now the local qubits of quantum information have become delocalized over some number of degrees of freedom. And if the scrambling circuit has depth which scales as log L, where L is system size, or larger, then one actually finds this kind of phase diagram. That is, if for fixed T over L as a constant, if one takes the dissipation strength to be sufficiently small, then this mutual information is actually maximal. Information is perfectly protected in the system, even though it's undergone many interactions with this dissipative environment. Whereas in, if the dissipation strength is tuned above some threshold, the information is completely lost. So one can think of this mutual information as having a sort of step function like behavior for fixed T over L as one tunes P. Okay, right. So this phase transition, unfortunately, I think in the interest of time, I won't have the ability to describe the reasons for this in so much detail, or really at all, but I would encourage you to look at our paper. The reason for this phase transition comes, the motivation for thinking about this actually comes from thinking about random quantum circuits, where we can understand the behavior of quantities like this mutual information, but averaged over ensembles of unitary circuit evolution, where each unitary gate is independently chosen from a measure like the Haar measure. And in that case, we can get some analytic control over these problems. And there, one actually is able to say something quantitative about the nature of these phase transitions and gain some intuition for why this is the case. Numerically, we also actually see this transition in Clifford quantum circuits in qubit chains with boundary noise. The critical dissipation strength is extracted by looking at sort of the scaling behavior of this mutual information, assuming some kind of scaling function that is obeyed by the mutual information near the phase transition point, and performing a kind of scaling collapse. An interesting open question here actually is that the scaling collapse of this mutual information near the phase transition is consistent with some critical exponents for the continuous transition that I mentioned, which don't actually match what we think the analytic prediction for what these exponents should be. So it's still an outstanding question what the nature of this transition is. Nevertheless, I bring this up because I think this is a very interesting setup, boundary noise with bulk unitary evolution, where it's really just a property of the mixed state that's produced by this open quantum dynamics that needs to be studied in order to detect this phase transition in a real quantum simulator. And it's a coding transition in a very similar way to the measurement-induced phase transition, which would be very exciting, I think, to detect and actually to see. Okay, so let me kind of skip maybe to the summary, just to bring up some questions that move on beyond the two areas that I discussed. So really, just to review, I've introduced two, I think, new examples of how adaptation and dissipation can induce new kinds of mixed state quantum orders and phase transitions. The first is involving constant depth protocols, where measurements and adaptation and feedback are used to foster mixed states with criticality, long-range entanglement, long-range order that nevertheless coexist with extensive entropy. And outstanding questions here, there are many, but some that I put up on the screen. One is, what's the power of adaptive quantum circuits with non-local communication? What's the range of mixed states that can be produced? I think is still an outstanding question, particularly in higher dimensions. The critical mixed states that are produced through these protocols, it's not clear what properties that they have that are actually universal or not universal. Whereas we have an understanding of universality in pure states at quantum phase transitions, continuous phase transitions, a similar understanding for critical mixed states, I think, is still ongoing and being developed. Can we use this kind of intuition to prepare other kinds of higher dimensional long-range entangled states more easily in mixed states that might be very hard to do in the context of pure states? So for instance, we don't have adaptive protocols to produce pure states that exhibit certain kinds of topological quantum order in 2 dimensions. It would be very interesting if we could produce mixed states that had some kind of long-range entanglement that is reminiscent of that in a much easier way. And related to the second area, there's this quantum dynamical phase transition, this coding transition due to the competition between unitary evolution and dissipation. One, I think, outstanding question is whether there are actually decoders for the coding phase. So in the phase where information is protected within the system, are there actually decoders that one can write down that are efficient, where one can recover that information? Or is it just the case that we know theoretically the information lives in the system or is lost in the environment? And what about bulk dissipation, especially when that bulk dissipation is localized at particular sites in the system, et cetera? And more generally, harnessing the ingredients that come out of thinking about random quantum circuits that have given us this intuition to understand boundary dissipation and its competition with bulk chaotic evolution, harnessing that to make more statements about open quantum many-body evolution in one and higher dimensions, I think is, to me at least, a very, very sort of interesting question. So with that, maybe I'll stop and thank you for your time, and to everyone for coming.
Yeah, thank you, Sagar, for the really nice talk and presentation, especially giving us a nice motivation and then a deep dive into the cluster state and connecting it to Hamiltonians and many-body physics, because I think a lot of people in this audience probably have seen it much more from the measurement-based quantum computing. So it's nice to connect it to gapped and topological phases and so on. This was also a great, actually, segue also. I think in 2 or 3 weeks we're going to have a talk from Elisa on a project we did actually with me and the team here on preparing cluster states at up to 100 qubits in experiments, trying to see what the errors do, and then using measurements and feed-forward adaptive circuits to prepare GHZ states or teleported CNOT. So this is a great segue into that. So folks, great connections here on the seminar series.
Yeah, that's really great. Yeah, I'm excited to hear that talk. Yeah, to see it.
Awesome. So maybe first question here from Hong Yao. It seems you can create mixed state long range order from adaptive regimes from the symmetry protected topological phase, or prepare larger SSB states or in trace out portion of the systems. Which one is easier?
So the question is whether, let me make sure I'm understanding correctly, whether it's easier to produce long-range entanglement or long-range order. Is that the question?
And Hong, feel free to clarify here in the chat. But I guess it's maybe you can take it as a broader question of, we've seen that there are a couple of ways to create states or create different classes of states. Which are the ones that are really easy and which are the ones that are really hard? And I guess that in itself might have 2 branches. One is theoretically and scaling wise, and the other is actually in an experiment where you have to worry about the faultiness of certain components.
Yeah, I think that's a really interesting question, and like you said, Zlatko, it's a question that can be attacked in many different ways. Let me just say one thing, which is first of all, which is that the state that is input into the adaptive protocol matters a lot, right? So if I mentioned that if I give you in one dimension a critical quantum state, then I can do some, I can obtain some very exotic critical mixed states with interesting negativity, scaling, and long-range entanglement and extensive entropy. But of course, preparing that critical state might be hard on a quantum simulator, right? So maybe of interest, potentially of more interest, might be that in higher dimensions, we believe that a gapped quantum system, which might be a little bit easier to prepare, can actually be put into an adaptive protocol to get a critical state, right? So they're taking into consideration how hard it is to prepare the initial state is very important. So the example that I provided where we obtain long-range entanglement in one dimension, there the long-range order in that mixed state also signaled the presence of long-range entanglement in the mixed state, right? So those 2 things were intrinsically related. I think in general, I don't have a good answer to this question because I don't have a good I don't have a quantitative connection between the amount of classical information that needs to be communicated and the amount of entanglement or long-range order that I get. And that's something we're still trying to develop and understand. I think for purely LOCC protocols, that might be understood. But here you can generalize this kind of adaptive setup where it's not actually exactly LOCC anymore also. And there we still know that in 1D, you can't get critical states through this adaptive protocol when you start with a gapped quantum state. So let me leave it at that.
Yeah, it's nice. It's a good question, really. How much classical information? I think one thing we appreciate, Hong says, thank you, by the way. One thing I appreciated is that sometimes taking the classical processing overhead is actually significant.
Yeah, right. Mm-hmm.
These are, especially when you have this large states and you have many bits you measure, you have to be careful actually with even the classical side. Yeah. Great. I think seeing as we're more than 10 minutes over here, I think maybe for today, well, let's Okay, let's take one maybe last quick question, which is more of giving us intuition, and then we're going to have to wrap up. But folks, this will stay recorded, which is, you showed us preparing cat-like many-body quantum states with these measurement feed-forward adaptive circuits. Can you remind us or tell us an example where you can prepare also this kind of either cat-like state, or it's a stabilized subspace of a Hamiltonian and a dissipator? So if you kind of think of a quantum evolution where you do some little Hamiltonian evolution, dissipation, Hamiltonian dissipation, or it's the continuous version of a Lindblad with a Hamiltonian. Are there some good examples of like even easy examples of the kinds of dissipators that you might have that would give you also these kinds of steady state spaces? I know that might be a little bit of a tricky question, so feel free to also.
Yeah, I mean, off the top of my head, I don't have a good answer, especially for these long range entangled states. I don't have a good answer to that question. But I would guess, would involve some kind of non-local operations that in order to foster that kind of long range entanglement.
Yeah, it would probably have to be short ranged entangled.
Yeah, right. Yeah.
Good. All right, Sagar, I think with that, thank you for the wonderful presentation. We've I'm sorry we won't get to all the questions in the chat. Folks, thank you very much for being with us at episode 142. To know what's coming up, click like and subscribe. Sagar's talk will stay recorded, so you can always go back and watch it, but only live at noon Eastern time can we have a chat live. So Sagar, thank you, folks. It was a pleasure, and see you all soon.
Thank you so much.